Modern cosmology stands upon one of the strongest scientific frameworks humanity has ever constructed. Yet, remarkably, one of its deepest questions still remains unresolved. For nearly a century, independent observations across astrophysics, nuclear physics, thermodynamics, and Einstein's relativity have repeatedly pointed towards one remarkable conclusion. The universe we observe today was once far hotter, denser, and dramatically smaller than its present state. Contrary to our rough intuition, the Big Bang does not describe an explosion occurring inside empty space. It describes the expansion of space itself. Every sufficiently distant galaxy appears to be moving away from every other galaxy, not because matter is flying outward into some external void, but because the metric fabric of space-time itself continues stretching in all directions. If this expansion is mathematically reversed, the observable universe converges towards an extremely dense primordial state approximately 13.8 billion years ago. Within modern physics, the Big Bang remains one of the most rigorously supported cosmological frameworks ever developed, with multiple independent branches of science converging towards the same early cosmic history. Yet, an important distinction must be made. Big Bang successfully explains how the observable universe evolved from an early dense state. But whether it explains the absolute beginning of reality itself is where modern cosmology begins encountering a far deeper uncertainty. And this distinction becomes increasingly important as we move deeper into cosmology. The first major evidence comes from observing the light arriving from distant galaxies. In the early 20th century, astronomer Edwin Hubble discovered that light arriving from almost every distant galaxy appears to be systematically shifted toward the red end of the electromagnetic spectrum. To understand this, imagine an ambulance moving away from you. As it moves away, the sound waves stretch outward, causing the pitch to gradually drop. Light behaves similarly. Although this is often compared to the Doppler effect, the distant galaxies are not simply moving through static space like cars moving on a road. Instead, the wavelength stretches primarily because space-time itself expands while the light travels, gradually elongating the wave across enormous cosmic distances. The high-energy blue wavelengths slowly shift towards lower-energy red wavelengths. This phenomenon is called cosmological redshift. What makes this discovery special is a measurable pattern known as Hubble's law. The farther a galaxy is located, the greater its redshift becomes. This revealed something profound. Galaxies are not randomly moving outwards through static space, the space-time metric itself is expanding, carrying galaxies apart with it. And if space is expanding today, tracing that expansion backward mathematically suggests the universe must once have existed in a far smaller and denser state. The second and perhaps strongest confirmation comes from the cosmic microwave background radiation. In the earliest moments of cosmic history, the universe was unimaginably hot. Temperatures were so extreme that atoms could not exist. Electrons and protons existed freely inside an ionized plasma, while photons constantly collided with these charged particles through continuous Thomson scattering, repeatedly changing direction before traveling any meaningful distances. As a result, the entire universe behaved like a dense opaque fog. Light simply could not travel long distances because photons were continuously scattered in every direction. As cosmic expansion continued, the universe gradually cooled. Roughly 380,000 years later, temperatures dropped enough for electrons and protons to combine and form the first neutral hydrogen atoms. This period is known as the recombination epoch. At this moment, the number of free charged particles suddenly collapsed. Photons were no longer trapped by constant collisions. Once matter became electrically neutral, radiation decoupled and began traveling freely across space for the first time in cosmic history. That ancient radiation still surrounds us today, but something unexpected happened during this journey. As spacetime itself continued expanding, the wavelengths of those original photons stretched enormously through cosmological redshift. Light that originally existed as hot visible radiation gradually lost energy and eventually shifted entirely into microwave frequencies. What we observe today is essentially a fossil photograph of the infant universe. the oldest electromagnetic signal we can possibly observe. Even more remarkably, tiny temperature irregularities called anisotropies within this radiation later became the original gravitational seeds from which galaxies eventually formed. The third confirmation comes from elemental composition itself. Across the observable universe, roughly 75% of visible matter exists as hydrogen, while approximately 25% exists as helium. At first glance, this seems ordinary. After all, stars continuously convert hydrogen into helium through nuclear fusion. But there is a serious problem. When astrophysicists calculate how much helium stars could realistically have produced over the entire lifetime of the universe, the numbers fall dramatically short. There is simply far too much helium than what stars could have produced. The only explanation consistent with physics is this. For several minutes after the earliest expansion phase, the entire universe itself briefly behaved like a giant nuclear reactor. Temperatures exceeded nearly 1 billion degrees. Under these conditions, hydrogen nuclei rapidly fused to form helium before expansion caused the universe to cool again. This period is known as Big Bang nucleosynthesis. Here, the mathematical predictions made by this model precisely match the hydrogen-helium ratio astronomers observe today. Even more remarkably, when astronomers study extreme ancient gas clouds that remained largely untouched by stellar evolution, they still observe nearly identical primordial ratios, preserving a chemical fingerprint from the earliest minutes of cosmic history. Three entirely independent observations, one consistent conclusion. The observable universe once existed in an extremely hot, dense, and rapidly expanding state. Yet confirming early cosmic history does not automatically mean we understand the beginning itself, because uncertainty begins the moment we push further backwards. Scientific success does not imply complete understanding. The Big Bang model works well when describing cosmic evolution after the earliest measurable fractions of a second. Its deeper difficulty emerges when extrapolation approaches the beginning itself. As the equations of general relativity are pushed backward, the space-time collapses toward what mathematics calls a singularity, a region where density approaches infinity and known physics completely breaks down. This is not a discovered physical object, it is a warning that our equations themselves stop describing reality beyond this boundary. A second challenge appears through cosmic uniformity. No matter where scientists observe the sky, the universe appears astonishingly similar in temperatures on extremely large scales. This creates what cosmologists call the horizon problem. Imagine two people standing on opposite sides of Earth, never communicating with one another, yet somehow possessing exactly identical information. The early universe presents a similar paradox. Regions separated by billions of light years exhibit nearly identical thermal conditions. Yet, according to the ordinary expansion rates, light, the fastest carrier of information, would never have had enough time to travel between these regions. In other words, these regions were casually disconnected. So, how did the universe become so thermodynamically uniform? To reconcile this, cosmologists introduced cosmic inflation. The idea proposes that before ordinary expansion began, the universe experienced an incredibly brief phase of exponential expansion, possibly lasting less than 10 to the power minus 32 seconds. Before inflation occurred, the entire observable universe occupied an extremely tiny region where matter, radiation, and quantum interactions remained in direct casual contact. Everything remained close enough to exchange energy and gradually settle toward thermal equilibrium. Then something happened. Driven by a hypothetical high-energy quantum field called the inflation field, spacetime itself expanded exponentially at a rate far exceeding normal cosmic expansion. Not matter moving through space, space itself stretching faster than light in that 10 to the power minus 32 seconds. This does not violate relativity because Einstein's speed limit applies only to objects traveling through space-time and not for the expanding space-time itself. The sudden inflationary expansion violently stretched the once tiny uniform region into an enormous cosmic volume. Regions once neighboring each other became separated by billions of light years. So the universe appears remarkably uniform today because those distant regions were once physically connected before inflation rapidly separated them. Inflation elegantly solves the horizon problem, but modern physics still does not know what exactly triggered inflation, what the inflation field physically is, or why inflation stopped precisely when it did. A third challenge lies in cosmic accounting. When physicists calculate galaxy rotation curves, gravitational lensing effect, and accelerating expansion of the universe, visible matter explains only about 5% of the required energy budget. The remaining 95% appears to exist in invisible forms we infer indirectly. These unknown components are labeled as dark matter and dark energy. The equations work, yet most of what sustains the universe remains physically unidentified. Finally comes the deepest limitation. If the Big Bang represents a physical event, what determined its earliest boundary condition? Current cosmology reconstructs evolution after the earliest measurable epoch. What preceded that boundary remains unknown. And this opens the possibility that the Big Bang may not represent the absolute beginning of reality, only the earliest horizon currently visible to physics. As physics approaches the earliest boundary of Big Bang, several advanced frameworks begin emerging. None have replaced standard cosmology, but each attempts to answer one deeper question. What if the Big Bang describes only our observable beginning, not the beginning of the reality itself? The most scientifically developed extension begins with cosmic inflation itself. Some physicists propose that inflation never stopped everywhere. The inflation field may have remained trapped in a temporary high energy state called the false vacuum. When this unstable state suddenly is changed into a lower energy stable state, inflation stopped in that region. Matter and radiation then began forming, creating what physicists call a bubble universe. This process is known as bubble nucleation. Under this framework, our Big Bang may simply mark the birth of one cosmic bubble inside a far larger multiverse. Its greatest limitation is that these other universes may always remain beyond our observable horizon, making the idea extremely difficult to test. Yet, inflation itself may not be the deeper explanation. Another possibility removes the singularity entirely. Instead of beginning from nothing, a previous universe may have existed before ours. As the early universe contracted toward extreme density, some quantum gravity models such as spacetime may resist collapse near Planck density, the smallest physically meaningful scale. Within loop quantum cosmology, spacetime itself becomes quantized into tiny discrete loops. At extreme compression, quantum gravitational repulsion may prevent singularity formation and trigger a rebound outward. Other frameworks, such as the egg-paratic universe, propose that our universe exists on a higher dimensional brane where repeated brane collisions trigger successive Big Bangs. In this picture, the Big Bang was not an origin, it was simply the latest bounce. Its largest challenge lies in entropy, since repeated cycles must continuously confront thermodynamics' steadily increasing disorder. But some theories challenge an even deeper assumption. What if time itself is not behaving the way we imagine? Einstein's relativity introduced a deeper counterintuitive possibility. Space and time combine into a four-dimensional structure known as Minkowski's spacetime. Relativity revealed something extraordinary. There is no universal now. Through relativity of simultaneity, observers moving differently through spacetime may disagree entirely about which event occurred at the same moment. Even more strangely, time itself physically stretches through time dilation under velocity and gravity. This led some physicists towards eternalism. Under this interpretation, past, present, and future all coexist simultaneously inside a deterministic space-time structure. Humans perceive time as flowing. Reality itself may simply exist as a complete four-dimensional block. The Big Bang would then represent not the beginning of existence, but merely one coordinate inside spacetime itself. Its greatest conflict appears when quantum mechanics introduces probabilistic futures that resist fully predetermined reality, but quantum gravity introduces something even stranger. Quantum gravity introduces a radical possibility. Time itself may not be fundamental. The Wheeler-DeWitt equation, which attempts to unify quantum mechanics with gravity, functions without explicitly requiring time. This has led some physicists toward an extraordinary conclusion. At the deepest quantum level, reality may exist in a timeless state. Mechanisms such as page order suggest time may gradually emerge only through quantum correlations between interacting systems. In other words, time may not exist independently. It may appear only when different parts of reality begin interacting with one another. If correct, asking what existed before the Big Bang may become physically meaningless because time itself may not yet have existed. Its greatest difficulty remains experimental verification near inaccessible Planck scale physics, but some theories go even further. Quantum physics allows bizarre events. Particles sometimes appear in locations they classically should never reach. This phenomenon is known as quantum tunneling. Some cosmologists propose the universe itself may have emerged through a similar process. Importantly, nothing here does not mean absolute physical nothingness. It refers to a quantum vacuum state, a seemingly empty state where temporary particle creation continuously occurs through quantum fluctuations. Under quantum cosmology, the universe itself may have simultaneously emerged through such a tunneling event. No classical cause may have been required. The challenge lies in defining what nothing physically means, since quantum vacuum states themselves already possess mathematical structure. Yet some models remove the need for any true beginning entirely. Proposed by Roger Penrose, this model suggests the universe never truly ends. Over unimaginable timescales, stars die, black holes evaporate through Hawking radiation, eventually leaving behind a universe dominated almost entirely by radiation. Penrose proposed that, under such extreme conditions, physical scale itself begins losing meaning. Through conformal geometry, an infinitely expanded old universe may become mathematically identical to an extremely compressed new beginning. The distant future of one universe may directly transform into another Big Bang. Penrose proposed faint structures called Hawking points inside the cosmic microwave background as possible remnants of the universe before ours. Its greatest challenge lies in observational disagreement, since these predicted signatures remain unconfirmed. But some physicists question something even deeper. Is spacetime itself truly fundamental? The holographic principle emerging partly from the black hole information paradox suggests our three-dimensional universe may not fundamentally be three-dimensional. It proposes that all information describing a region of space may actually be encoded on its lower dimensional boundary. Frameworks such as ADS-CFT correspondence suggest that higher dimensional reality itself may emerge from information stored elsewhere. If correct, the universe we experience may simply be a projection of deeper information structures. Space itself may not be fundamental. While mathematically powerful, experimental confirmation remains extremely limited, yet some frameworks push even further backwards, toward a stage where space itself may never have existed. This model proposes something even more radical. Before spacetime existed, reality itself may have possessed no distance, no dimensions, no geometry, and no physical structure. Some physicists call the transition into geometry geometrogenesis. Frameworks such as quantum gravity suggest reality may initially have existed as a discrete quantum network without physical shape. This idea traces partly to John Wheeler's principle, it from bit. The Big Bang would then represent the moment geometry itself condensed into existence. Its greatest challenge remains explaining how geometry emerges without already assuming geometry itself. Yet some physicists argue reality may be deeper than physical structures altogether. Some argue mathematics does not merely describe reality. Mathematics itself may be the reality. Under Max Tegmark's mathematical universe hypothesis, matter, energy, space, and time may simply represent expressions of deeper mathematical structures. The universe itself may behave as a self-consistent equation, expressing itself physically. Its greatest limitation remains testability, since any possible observation can simply be reinterpreted mathematically. And beyond physics itself emerges the most philosophical possibility. The most philosophical proposal suggests physical reality itself may be artificial. Our universe may function like an advanced computational system where space, time, energy, and physical laws simply represent programmed information processing rules. This idea is partly motivated by Nick Bostrom's Bostrom trilemma, arguing that sufficiently advanced civilizations may eventually simulate conscious realities indistinguishable from physical existence. Under digital physics, reality itself may be computational rather than physical. While logically fascinating, this framework currently lacks direct physical evidence, and unlike other cosmological models, this remains largely philosophical speculation. Modern cosmology has reconstructed the history of the observable universe with extraordinary precision. The Big Bang remains one of humanity's greatest scientific achievements. Yet, the closer physics move toward ultimate origins, the more certainty begins dissolving. The singularity remains mathematically unresolved. Inflation explains much, but not everything. Dark matter and dark energy dominate cosmic behavior while remaining physically unidentified, and multiple theoretical frameworks now allow reality itself to extend beyond the earliest boundary we currently observe. This does not weaken the Big Bang, it transforms what the Big Bang may represent. Perhaps it was not the beginning of everything, but marked only the beginning of our observable cosmic chapter. The deeper question now becomes unavoidable, not simply how the universe began, but whether concepts like beginning, origin, before, and even time itself remain limited human descriptions applied to a reality far deeper than present physics can fully describe. The universe may not begin where our equations currently stop, it may simply begin where our understanding does. And beyond that boundary, what we currently call the beginning of existence may eventually prove to be the only another transition inside a reality far larger than present physics has yet learned to comprehend. Perhaps the most fascinating possibility is this: humanity may not be far from understanding reality because knowledge is missing. It may be that modern science has already uncovered many of the fundamental principles governing existence itself, and the final breakthrough may come when these scattered truths are finally connected into one coherent understanding of what reality has always been. But our exploration has only begun, because every unanswered question surrounding time, gravity, consciousness, quantum mechanics, information, intelligence, and existence itself may not be separate mysteries, but interconnected pieces of a far deeper scientific structure we are only beginning to assemble. Subscribe for our next queries and discussions. Let's seek knowledge, let's innovate to sustain. Nandri, Vanakkam.